Can you see my slide in slideshow? Is it in slideshow? It's just the PowerPoint presentation. Can you please inform me if it's on slideshow?
Makita pa yung side miss na ano,
Ah,
tawag dito, mga other slides.
hindi pa siya naka-slideshow. What about this?
Okay na, miss.
Thank you. Sige. So for this afternoon, we'll be discussing areas of plane regions. So these plane regions can be areas between a curve and an axis, a curve and another curve, or a curve and a line. So let's check first our learning objectives for this topic. So for our learning objectives, so at the end of the topic, the student should be able to find the area between the curve, the x-axis, and the two given ordinates. So these two given ordinates are actually the limits of integration. It sets the boundary of the area that we're going to determine, that area which is bounded by the curve and the x-axis. Now for the second objective, so students should be able to find the area between a curve and the x-axis where the ordinates are given by the points where the curve crosses the x-axis. So this time, we are to determine the point of intersection of the curve and the x-axis, and these points of intersections rather would be our limits of integration, because our area of concern is then bounded by these intersection points of your curve on the x-axis. And the last, you are to determine the area between two curves, or an area between a curve and a line. So we're going to do this step by step. We're going to start with the first one, the area between the curve, the x-axis, and the two given ordinates, which are the limits of integration. Now, let's first review on the definite integral. So, reviewing the definite integral and recalling the topic on numerical integration, that was our previous topic. It was discussed to you that the area under the curve for such non-elementary definite integral is actually the value when that particular definite integral is evaluated. So when you are determining the value of a definite integral, actually you are determining the area under the curve given in your integral. So the function that is given in your integral is actually the integrand. So the area under the integrand, or the function that is given in your integral, is the value of the given definite integral. And as such, you have in this part of the slide the review on the definite integral. So let's say, for example, you're given the function f, which is said to be continuous on the designated interval AB. Then the Riemann sum for the function on the said interval AB approach a real number limit I as n approaches infinity. So again, recalling the topic on numerical integration, the approximation of the area under the curve depends on, or the accuracy of such area depends on, the number of divisions, or the number of intervals that you have placed under the area of the curve. How many, let's say, trapezoids, or how many Simpson's area do you have under the area of your curve? So as we increase this n, the number of divisions, our approximation become near the, or becomes even closer to the real value. So this limit I of the Riemann sum for the function on the interval AB is called the definite integral of the function f from A to B, denoted by the given integral that you are seeing here. So the integrand is the function of x, the lower limit of integration is said to be a, and the upper limit is b. Okay. Now, let's say, okay, let me go back first. Now, let's go to areas under functions. So when you speak of areas under functions, these are definite integrals which are used to find the area between a function and the x-axis. Now the limits are the point at the start and in the end of the area you are asked to find. And if the curve is not drawn for you, it is often a good idea to sketch it to give you an idea of what you're looking for. Now, you were taught in your senior high and even in junior high school how to plot properly a curve. So knowing how to plot a given curve will give you an idea of the shape of the area and of the boundaries of the said area that you are determining when you are evaluating a given definite integral. So it is suggested that if you still have time, it would be proper that you plot the said area so you would know that particular area or the shape of that particular area. Okay. Now, let's say for example, you have this, integrate and substitute in the limits. Now, as you could see here, if you would like to, if I will annotate, this is the curve, this is our function, this is our integrand. So this is the integrand, the function that is written here after your integral sign. So that's your integrand. And it's x squared minus 6s plus 11. You are to determine the area bounded by this function and the limits of integration 1 to 4. So these 1 to 4 are actually values of x in which the area that you will be determining will be bounded on. So you're only going to determine the area starting from x equal to 1 to x equal to 4. Now, if you recall also that when we speak of x equal to 1 and x equal to 4, we are referring to vertical lines. And these vertical lines are this one. They are these lines here. So this is your line. If I will extend, this is your line x equal to 1. This is your line x equal to 4. So if you notice, it's okay. It's okay. You may notice that you have this line x equal to 4 and x equal to 1. And it is the limit of your integral. They are the limits rather of your integral. And this is the function. So this is the first objective, that you will determine the area bounded by your curve, your integrand, the limits of integration representing these two vertical lines, and of course this x-axis here. So this is your x-axis. So the area that you are trying to determine is this particular area shaded in yellow. Now, if you tried to before, it's just if anybody by any chance studied in advance, and if you're holding an integral book right now, determining area requires as well, class, that you will draw your differential element. In our case, we draw our differential element in this manner. It's a vertical differential element because whether we have this point here or we have this point here, we have this point here or this one and this one and this, all throughout the area that we're trying to determine, this differential element would be the same. It's referring to the same function and this x value here. Okay, it does not change. It could also be that if you want to choose, you can choose a horizontal differential element. But if you do that, just for illustration purposes, I'd like to show to you. If you choose a horizontal differential element, like this, say for example, I draw this differential element. It's okay until this part only. Before you reach this curve, because once you already reach this part here, this part of your differential element and this part will not be the same as this one. Because in here, what you have is this line. In this region here, you have this line x equal to 1 and x equal to 4. Whereas in this part here of your area, you have this line x equal to 1 and this curve already. So the inconsistency in determining the length of this differential element could be avoided if you use something that is vertical. Now, if you will allow me to speak in Ilonggo class, kung ang imo gingamit nga differential element horizontal, ang x equal to 1 kag x equal to 4 nga representation sang length sang sini nga differential element will only be good until this part here. Because once you already in here or in here, it's not anymore true. Because the length of your differential element would be now the difference between the x of this particular curve and the x of this line. Whereas in this particular region, it's the x of this line and the x of this line. So it's inconsistent. When you choose a vertical element, and especially if you want to determine the area under your curve, your intervals or your limits of integration and the x-axis, it is always suggested that you use the vertical element. Why am I discussing regarding the differential element here? Because it's the first step in determining the area of any region. You write properly your differential element. That way you will know whether your representation of your differential element will be correct wherever you are situated. So let's see if we have the vertical element here. This is our differential area. So the width of this differential element is dx because it's parallel the x-axis. Its length is dy. So it's y dx. Now look, whether I'm in this part or in this part, it's still the curve minus the line. It's still the curve minus the line. So it's consistent. There won't be any inconsistencies on how we will determine the area of our region under the curve. So in here, you could see that when you determine the integral, you are actually getting the area of this differential element. And it's represented by y dx. The dx is already here. And this y is actually the length of this line, this differential element. So that would be the y of this curve minus the y of this line, specifically. So I'll say y of the curve minus the y of the line. Now, what is the y of the curve? This is the y of your curve. So it's written x squared minus 6x plus 11. What is the y of the line? Now, if you recall our discussion last meeting, the x-axis is represented by a line y equal to 0. So it's just like you subtract 0 from x squared minus 6x plus 11. So the appropriate representation of y dx actually is the y, which is y of the curve from this point here, minus y of the line. So that would be the y of this differential element times dx. If it's integrated from 1 to x, then you are determining the area starting from x equal to 1 to x equal to 4. You get it? So what you see here is a direct way of determining the integral, but how or where was this based on? It was based on this formula. Y dx where y is yc minus yl. The manner of subtraction, class, is always the uppermost point to the lowermost point. You get it? Uppermost point minus lowermost point. So the y of the curve minus the y of the line, which is 0, is this one. Now, if you notice, class, the process of integrating this is very simple. You just use power rule here, and you just simply drop the t for the 11. So that would be 11x. After you have already the answer, after already determining the answer to this, you just substitute the limits the way it was discussed under definite integral. So your answer in this case for the area under this curve, that would be 9 units. Do you have any questions for this particular example? So you always first draw the differential element, And your differential element, or specifically your differential area, should be consistent wherever location you're going to draw it. In our case, if it's drawn here, it's still y of the curve minus y of the line. If it's drawn in here, it's still y of the curve minus y of the line. So it's consistent. But most of the time, especially if you want to determine the area under the curve, the x-axis, and the limits of integration, it's a vertical differential element, or our differential area is vertical. Now, do you have any questions? Okay, so I hope everything is clear. I'll clear my markings here. Then we proceed. Now, what about this one? So example number 2. Okay, your curve is x cubed minus x plus 3, and it's like this. It would be best if you have an idea on how the curve look like. So it look like this if it's drawn on our Cartesian plane. Now, we're still going to determine the area bounded by this curve, the limits of integration -1 to 1. So this is actually, okay, I'll draw again. So this is actually your line. This is your line x equal to -1. And this is your line x equal to 1. So your limits of integration represents these two vertical lines that is also at the same time that are representing the boundary of the area under the curve and the x-axis. Okay, now if you're going to draw your differential element, it would be best that you have drawn it, you draw it vertically. Because if you draw it horizontally, your differential element will be inconsistent in terms of its length. So if you draw it vertically, this is still dx, because this one changes from -1 to 1. So you're going to integrate in terms of x, so that is why it's dx, and this is your y. Now your y is still the y of the curve minus the y of this line, which is y equal to 0. And you notice here, using the formula y dx, this is now your representation of the integrand. The y of the curve, which is x cubed minus x plus 3. And this is your dx already. And you just need to integrate this one. If you will integrate this one, it will give you this answer. And you just substitute the limits -1 to 1. By the way, this is -1 here, and this is 1. Okay, there's a typo error there. It went up. Okay, if you substitute your limits, the upper limit first and then lower limit next, your answer for this area is 6 units squared. You know it has to be squared because when you speak of the area, it has to be squared. Now, any question? The first two examples, class, are easy because the limits of integration are already set. So it's already given as -1 and 1 in this case. The other one is 1 to 5. Now it's difficult, or it's a little bit challenging if the limits of integration are not specified and you are the one who's going to determine it. So that's very important. That's the portion, or that's that part wherein it's very important for you to know how to draw your curve. That way you can visualize the area that you are determining. Now, any questions so far in the first two examples? Okay, so there's none. So I will proceed. If there is none, if there are no questions, then we proceed. Now, beware of curves that go below the x-axis. You must calculate where the function crosses the x-axis, and this is the part where you need to determine the point or points of intersection of your curve on the x-axis. You need to calculate the area above and below the x-axis, take note, separately. So meaning you don't add the areas as in literally add, but rather separately determine them and consider the area located below the x-axis as its negative. So you have to place a negative sign before the integral of the area that lies below the x-axis. Now question, how would you know that such area lies below the x-axis? That's the important part wherein there's a need for you to sketch your curve. Okay? Now, this is what we're going to do for the next example. Okay. Now, if f of x is positive for some values of x on a and b and negative for others, then the definite integral like this, the function of x integrated from a to b, represents the cumulative sum of the signed areas, meaning if it's above the x-axis, you put a sign positive to it. If it's below the x-axis, you put a negative sign before it. That is why it says here the sum of the signed areas between the graph of the function and the x-axis, where areas above are positive and areas below are negative. What does this mean? Let's say this is your function. You've drawn your function and you've noticed that an area, a part or one area of your function between itself and the x-axis is below the x-axis. This is area A. And the other is area B, above the x-axis. When you determine the sum of these areas class, you need to place a negative sign before the integral representing this area. Why? Because when you evaluate this particular integral, your answer will be negative. And there is no area that is negative. So to make it positive, you have to place negative before it. This one automatically becomes positive because it's above the x-axis. So it's important that you specify specify the areas. It has to be signed areas. Above is positive, below is negative. Now, question is, if you're going to represent these two as two separate integrals and then later on add their values, then there's a need for you to determine this point of intersection. You need to determine the point of intersection there. That way, this particular integral will be from A to whatever this point is. Let's say this is area A, dx, plus this one, the B, will be from whatever this point is to B. And you have here B dx. So there's a need for you to determine first this point of intersection if these two are already known. Now, based on what you have learned in high school, how do you determine the intersection of your curve with the x-axis? Who can tell me how will you determine the point of intersection of your curve with the x-axis? It's very elementary and it should have been learned in high school. How do you determine the point of intersection of your curve with the x-axis? Okay, I'm glad I have one here. Just set y equal to 0. Very good, Carlos. Mr. Gimbal. So Mr. Gimbal said that you set this y equation of yours of the function to 0. Then as much as possible, have this function factored. That way, the factors you can easily equate to 0 and find the point or points of intersection. Once you know already the points of intersection, these are the points that will be written in the limits of your integration, depending on how many areas you need to sum up. In our case here, we only have 2 areas, so you only need 2 sets of limit. Lower limit of the first is A to whatever is this. then the next will have the lower limit as whatever the value of this to be. Okay? So now it brings again back to the principle of knowing how to plot your curve based on its points of intersection on the x-axis. Now, do you have any questions? Okay, there's none. So we'll proceed to the next. Now, here we go. See this curve? This curve is actually x cubed plus x squared minus 2x. The way it's written here in our illustration, it's already factored. So we factor first the x, then you have x squared plus x minus 2. And that would give you these two factors, the x plus 2 and the x minus 1. Okay? Now, you said, Miss Ali, a while ago that it's important that we always set our differential element. So we set our differential element. So this is our differential element. Okay. Dx and y. Is this y consistent whether I'm here, I'm here, I'm here, I'm here, I'm here, I'm here? The answer, of course, is yes. It's consistent because it's the curve minus the line. In the case of this second one, if you draw a vertical element, this is still y, and this is still dx. This y is actually the negative of this y. Why? Because if you start always subtracting from the top to the bottom, you will have here, let's say this is y2 and this is y1. Your y1 is equal to y of the line minus y of the curve. Whereas your y2 is equal to y of the curve minus y of the line. What have you noticed? This is just the negative of this, right? So that's the reason why when you add the areas of these two, you place a negative sign before it because your y is still the same y as it is in here. The y that you used in here is the same as this one, only that it is negative because based on our procedure, it's always top minus bottom. And you have line minus curve, which is the negative of curve minus line. So for it to be consistent, you just simply have to write negative before the computation of the integral of this line. Now, how do you find the points of intersection? So Carlos said a while ago that you will set this equal to 0. If you set this equal to 0, the y equation of your function, your factored form, each of the factors will be equated to 0. So this point is your x equal to 0. This point is your x equal to negative 2, coming from x plus 2 equal to 0. So your x is negative 2. So you have another intersection here. And this one, x minus 1 equal to 0. So this is your x equal to 1. So this is how you came about with the limits of your integral. You have two integrals. The first one is should have the limits negative 2 to 0. It says here, substitute in the two sets of limits, negative 2 to 0. The second one is 0 to 1. Now, the equation of the function is still the same. Amo lang yun siya gyapon ang imo i-evaluate. O galing duha ka set of limits. For the first one, it's negative 2 to 0. For the second one, 0 to 1. However, you are to multiply it by negative 1 to make it positive. I'm referring to this one. The 5 over 12. So the 8 over 3 is for this one, it's okay because it's really positive. But this one is negative. So you have to place negative before it. When you substitute to this answer of yours, 0 to 1. So you have to place negative 1 before it. Or you have to multiply it by negative 1. So this will be now your answer. 37 over 12, or that would be 3 divided, 3 and 1 over 12. Now, do you have any questions? I'll give you 2 minutes to check whether you'll be getting the same answer. Please do check. And we'll continue with the next example while I'm also waiting here for questions if there are any. Okay, so check if you can get these answers here. If you process the same integral, actually the answer is already in here using 2 sets of limits. This one is positive, this one is negative area. How is it? Did you get the same answer? Do you know how to get the answer now? Now we go to example 4. The same thing, you will have an area below the x-axis and you will have an area above the x-axis. Find the area between the curve y equal to x times the quantity x minus 3 and the ordinates 0 to 5. So the ordinates 0 to 5 are actually this. So this is for x equal to 0 and this is for x equal to 5. Now, the thing is, you have to determine this point of intersection. So, as suggested in finding the point of intersection, this is just a review, you equate the equation of your curve to 0. So, you will get two values of x equal to 0 and x equal to 3. Because you equate x minus 3 to 0, so you will have 3. So, this is the other point of intersection. So for area A, that would be negative of the function integral. Your limits will be from 0 to 3. For B, at least B here, for B, that would be, since it's above the x-axis, that would be your function of x, dx. It's positive now. The limits would be from 3 to 5. The area total should be equal to A plus B. Now take note that A should have a negative sign before it because it's an area that lies below the x-axis. Now, if you have drawn your differential element here, this is 1, this is y dx. It's consistent within the area that you're going to determine. The same thing in here. If you draw a vertical differential element here, this is dx and this y, it's consistent. Curve minus the line in terms of the y. So yc of the curve, which is this, minus the y of the line, which is 0. In this one, it's y of the line minus y of the curve. So it's the negative of this. That is why you have negative. Okay? Now, if you will proceed to the next slide, this will be your two integrals. Okay? So for the A, this will be your function. Your function was expanded. So it's x squared minus 3x when integrated. And this would be the area A. So notice it's negative. So that's the reason you place negative before it to make it positive. For the B part, for the B part, it should be 3 to 5. So you have your 3 to 5, the same equation, substitute, you have this. So the total actual area is actually the negative of the area A computed plus the area B. And that's 13 and 1/6 square units. Do you get it? Okay, sige. So if there are no questions, we will proceed. Now, finding the area between two functions. So this time, we will determine not the area between the curve and the x-axis and bounded by the limits of the integration, but we find the area between two functions. So these functions can either be both curves, or one could be a curve, another one could be a line. Excuse me. So this is finding the area when the smaller area is subtracted from the larger. So integrate, substitute in the limits, then find the difference between the two. Okay, this is an example. The larger area minus the smaller area is the area that we're trying to find. Now, if I'm going to ask you, what's the largest area in this case? I'm going to ask you, what's the largest area? If I will ask, what's our largest area? The one with the diagonal line. Sige, I think I know what you mean. The largest area is this. I'll draw it above the statement here so you would have an idea. So this is the largest area, the shape of the largest area. This is your largest area. In here, this is the area I'm referring to. Okay, now that's the largest area. Sorry about my lines there. What's the smallest area that you need to subtract from this larger area to get the area in yellow? It's the smallest area. Smallest area is at that. That's the smallest area. If I use a different color, I'm not sure, green, it would be this. This again. So this green area subtracted from the red area will give you this yellow area. This is one way. There's another way, and it depends on you on what particular process you will use. As long as in principle, you're using the correct limits, and in principle, you use the correct formula in determining the area under the two functions. Okay, so this particular process is this, the larger area minus the smaller area. Now, let me first erase class so it would be clean. Now, if I'm going to ask you, what's the area, or what would be the formula that you will use in determining the area, the largest area? What formula will you use? You see here an integral. So it's 2x plus 1 from 1 to 4. So it's actually not a curve, but that of a line. So what area was determined in this case? This is it, huh? If you use integral, that area is this. This is the dx, and this is the y. Your y would be the y of this line, which is 2x plus 1, and the y of the x-axis, which is y equal to 0. That's the reason why you see here only a 2x plus 1. So you have here y dx for this. It's consistent because whether you're in this area, this region, this region, this region, or this region, this same differential element will be used. There's no inconsistency on how it should be represented in terms of the product of y and dx. So you could see it in here. But actually, class, it could also be determined using the area of a trapezoid. So you have a trapezoid here. You have this as the two parallel sides. And this is your height of the trapezoid. But since we're using integral calculus, so this is the area of this trapezoid. Okay? Using integral calculus in determining the area of this trapezoid using this differential element here. So y dx, the limit is x equal to 1. This is your x equal to 1 line and x equal to 4. Okay? What about the smallest area? So, kaina, I've drawn the smallest area. And that area would be this. I'll use a different differential element color so you will not be confused. This is the second differential area. Okay, so this is your dx still, and this is your y. Your y here this time is not the y of the line, but rather the y of the curve minus the y of this line, which is 0. This is the y of the curve. What is the y of the curve? X squared minus 3x plus 5. So this is still y dx. But this time, that of the curve minus that of the line, which is 0. The limit is still 1 to 4 because we have here from 1, from 1, this is where 1 is, and 4. Our yellow region is to be determined on the limits 1 to 4. At the same time, it represents the point of intersection of our curve and our line. Okay? If this 1 and 4 is not given, you should be able to find the point of intersection of this curve, x squared minus 3x plus 5, and this line, 2x plus 1. I will discuss that later. But for now, this is how we determine the area of the yellow region. The larger area minus the smaller area. Then you just do your integration, substitute the limits, and this is your answer. But there's another procedure which I will be discussing if you don't have any question in this part. Do you understand this particular solution? Okay, so I'm happy that you understand. The bigger area minus the smaller area gives you the yellow area. But there is another straightforward way of determining this area of the yellow region. I'll clear my markings and show it how it's done. You go directly to the region that you have here, the one shaded in yellow. I'll use a different color, let's say blue. I'll use the vertical element. Okay, this is my vertical element. This is y, and this is the x. Okay? Now, what is the y of this vertical element from this part here until this part here? It's consistent. Why? Because you start with the upper portion minus the lower portion. You need to subtract. And in that case, the area that you're determining would be the y of the line minus the y of the curve, dx, on the limit 1 to 4. Now, isn't this the same as this one, only that it was separated when it was integrated? So this is for your line minus this is for your curve. So it's more straightforward rather than having to think of what's the biggest area minus the smallest area. So you use directly the area of the differential element that you have drawn within this region that you are to determine the area. So that's it. So you have line minus the curve. And limit is 1 to 4. So basically, we'll get the same answer because it's the same function that you're going to place in here. Now, the question a while ago is, how do you determine this 1 and 4 if it's not given? What if it's not given and you are the one, or simply the problem will be asking you, what's the area between the curve x squared minus 3x plus 5 and the line 2x plus 1? You don't have any limit. How do you determine the limits of integration? Everybody? How do you determine the 1 and 4? Because the problem is just simply asking you what's the area of the region or the area of the intersection of the line and the curve, giving the equation. So what would you do to find the points of intersection? So meaning you're to find this. This is x equal to 1 and this is x equal to 4. How do you find it? Anybody? How do you find the intersection of two lines? It's the same as this one. In here only, you're going to get the intersection, the points of intersection of a line and a curve. In high school, you were taught how to determine the points of intersection or the point of intersection of a line because it has only one point of intersection. How? How? Easy. What you're going to do is substitute the y equation of the line in here. What would you do? I'll erase my markings first so that I will have bigger space to compute. So what you're going to do is this. You'll just use red. You could be seen. Equate this one and this. They are all y's, right? The y of this point, at this point, for the curve and the line is just the same. So you equate. So you have 2x plus 1 is equal to x squared minus 3x plus 5. So you'll have one quadratic equation, x squared minus 5x plus 4. Is this factorable? The answer is yes. It's x minus 4 and x minus 1. You equate this x minus 4 to 0, you will have this point of intersection, which is x equal to 4. And you equate x minus 1 to 0, you will have this point of intersection, which is x equal to 1. That's how you find the point of intersection between a line and a curve, or between curves. You just equate their two equations. Why equate? It's because I've said at this particular point of intersection, the curve and the line has the same x and y. Same thing in here. So that is why you equate. Do you get it? If the limits are not given, it is also possible for you to determine the points of intersection. Any question? So no question? So this is the fifth example regarding area between two functions. Now we'll have another one. So calculate the area of the segment cut from the curve y equal to x times 3x, rather 3 minus x, by the line y equal to x. Okay, so we will use the same principle that I have outlined to you in the previous example. Same thing. This time you will be more straightforward. We will determine the area of this gray shaded region. So I'd like to draw my differential element vertical, because I know that if I'll make it vertical, my y in here and my y in here at the bottom will be consistent whether I'm in this region, in the middle part of the region, or in the topmost part of the region. I will represent this as my y, and this is my dx. But first, we are to determine the point of intersection of the line and the curve. Okay, calculate the area of the segment cut from the curve y equal to x times the quantity 3 minus x by the line y equal to x. So this is this line here. Now, the value of this one and this, you need to determine just in case it's not given. But however, it's already given in here. So just in case this is not given, the point of intersection or the boundary, the boundary of the line and the curve in here in which you're interested with the area, you just equate again the equation of this y and this y in here. So that would be x equal to, so you will have here 3x if I will distribute and minus x squared. You have that 3x minus x squared. Okay, I'll transfer this one here. So this would be 0. And I will have 2x minus x squared. I will have 0 equal to, wait class, y equal to x. Okay, so that's it, 3x minus x squared. So if I transfer it here, it's 2x. So if I factor, I will have x and I will have 2 minus x. So in this case, class, this particular point of intersection is 0. Your x will be 0 and x equal to 2. If you equate this 2 minus x to 0, so your x is equal to 2. If x is equated to 0, it would be 0. Okay? Now, however, it says here, sketching both curves on the same axis and setting y equal to 0, make the curve y equal to x times 3 minus x, quantity 3 minus x, cut the x-axis at 0 and 3. Now, this 0 and 3 class, if you have read it correctly, this is the 0 that is being referred in here, to x equal to 0, and this is the 3 that is being referred in here. So it is not actually the limit of integration for the area that we're trying to determine. The area that we're trying to determine is just this area, which is bounded by x equal to 0 and x equal to 2. But that is true that this particular curve will cut your x-axis on this point 0 and 3. So you are to determine this area. Okay? You will not use these limits for this area, but rather you will use this particular limits here, 0 to 2. So I'd like to write here the answer. So we'll have the area that we're interested is the integral of, so you will have y dx, limit is from 0 to 2. Okay? Then what is that y? The y of this curve, which is 3x minus x squared minus the y of this line, which is x. Okay, integral, and you'll have here dx. Feel free to interrupt if you cannot follow. So you have that. Then we will simplify. We have 0 to 3 again. And you will have here 2x minus x squared dx. So you'll have, if you integrate this, you will have x squared. And you will have here x cubed over 3. You will have 0 to 2. Okay, I'll place here 3. So that would be 2. Okay, and then you will substitute the limit. So that's 2 squared. That would be 4. And you will have here 8 over 3. If you substitute 0 for both of this, that would be 0. So can you give me the answer for our area here? 4 minus 8 divided 8 over 3. That would be 4/3. Okay, or 1 1/3 square unit or square unit. So this is the area of this area. Now, before I go to the next slide, do you have any question as to what we have done in here? We are determining this area here, the gray area, in this solution that is presented to you. Okay, no question? Sige. So I will now clear my markings here and proceed to the next slide. Actually, the solution is in here. So the line y equal to x goes through the origin and meets the curve y equal to x times the quantity 3 minus x at the point P. So that's correct. Your line y equal to x intersects this curve at point P. At P, the y coordinates of both curves are equal. So this is what I have shown to you. Okay, I have done that already in the previous part. Okay, this is the step-by-step process of what we have done in the first page of our solution, for example, number 6. Okay, so I will clear my markings here and proceed. So the shaded area in the diagram is the area under the upper curve, and the graph of y equal to x times 3 minus x. And between the x-axis and the coordinates x equal to 0 and x equal to 2 minus the area under the lower curve, the line y equal to x. And between the x-axis and the ordinates x is equal to 0 and x equal to 2. The process that is given in here, class, is the same process as process number 5, wherein you are to determine the area under the curve, so the entire area under the curve, and you are to determine the area under the straight line. It's just the opposite of the first part. So in sample problem number 5, we determined the area under the line, then we subtracted the area under the curve. In here, we subtracted the area under the line from the area under the curve. If you use this procedure, you'll still be getting the same answer, which is 1 1/3, or that would be 4/3. The solution that I have shown to you is a more straightforward manner of determining such area. Now, I'd like to go back to the illustration just to point out to you why the area under the curve minus the area under the line in this case. So remember that this is our region. This is the region that we're interested. So the bigger area in this case is the area of the curve, this one, this entire thing. Wherein you have here 0 and 3 for the x. So this is for the curve. As for the line, the area under the line, it would be just this one. This is the area under the line. So the area under the curve, but since we're only until 2 in here, so we'll just, instead of integrating from 0 to 3, you will only integrate until 2. Because you're only interested in this one, this part here. Of course, it's the area under the curve. This one, until only x equal to 2. If you subtract this particular triangle, this will also be until only x equal to 2. So this area, I like to use the blue colored ink. So this area, just like this same area, is not included when your limits of integration is just from 0 to 2. Yeah, I'd like to go back to that. So for this line here, it's also from 0 to 2. So area under the curve minus area under the line will give you this gray area here. So you get to rather determine this area in the gray region only. You get it? So the process that is illustrated in this set of slide of yours is bigger area determined using the limit 0 to 2, that's the area under the curve, minus the lower area, limits also 0 to 2, under the line. That would give you this gray area. Nonetheless, the one that I've shown to you will give you the area faster, and it's more straightforward. Okay? Any question? Okay, I'll clear my markings if there are any questions. So this is the thing, that's the other solution that you can also refer back to. Whichever of the two procedures you're comfortable, I'm referring to example 5 or 6 and 6, it's up to you. But it will still give you the same set of answers. So notice that your limits of integration is only 0 to 2. Although your curve touches your x-axis until x equal to 3. But you're not interested in that because the segment is only until x equal to 2. The segment that is being referred to is this gray area. Okay, so we'll have the case of inconsistent boundaries. What is this? So let me read this one. If you look at the area in figure A, this is figure A, class. The upper and lower boundaries are not the same for the left portion of the graph as they are on the right portion. So if you notice, if I'll make, let's say, I'll annotate so it will be clear. If I will look in these two regions as this region here, okay, this is one region, for example, and this is one region here. Okay, so it's hard to really outline. So you have two separate regions here. Now it says here the upper and the lower boundaries are not the same for the left portion of the graph and the right portion of the graph. So if you do it like this class, you have one in here and one in here. If you make a vertical element, I'll use a different font, a color, no, not blue, yellow. Even if you consider this as an entire figure, you have this one here. If you have this vertical element, so you'll have dx, and this is y. In this part, you will have the y of the curve minus the y of the curve. Cannot be, right? Or in this part now, that's the left part. So in here, if your differential element is already drawn in this part, you'll have the y of the curve and the y of the line. More so, if you're in here, until here, you have the y of the curve until the y of the line. But in here, you have the y of the curve minus the y of the curve. So there is inconsistency whether you are in the left portion and the right portion if you're using the vertical. If you're using the vertical strip or differential element, and it's just one differential element for this entire area. Okay? Now let's see. I will just create my markings here and we'll proceed drawing. So there is already an inconsistency. So the upper and the lower boundaries are not the same. So lain ang y sa babaw, lain ang y sa dalom, there is a left part kag sa right part sa outon area. So whether we consider it as one area or we consider this as one area and the other area in here, it would still be the same inconsistency. The upper part and the lower boundaries of your bounded area are not the same. On the left, the x equal to y squared curve is the upper and lower boundary. True. Kaina, ipakita ko. So in here, loko naman liwat. This is our differential element. What does it say? On the left, this is the left, the x equal to y squared. This is your curve. This curve here is x equal to y squared curve is the upper and the lower boundary. Babaw niya kag idalom puro tanan curve. So it's y squared. On the right, you will have x equal to y squared curve and the lower boundary is the line y equal to x minus 2. So there is already inconsistency. So therefore, in order to calculate the area using x as our variable, we must divide the region into two pieces. So there's a need for us to divide it into two pieces. Find the area of each, then add those areas to find the total area that is illustrated here below. So what's done, you just clear my drawing there. What's done is you have divided the area into this. You have this area 1 and you have this area 2. In here, and this the red. If you will have this as the vertical element, you use the vertical element. The upper portion is bounded by this curve, which is y equal to the square root of x because x is equal to y squared. So in terms of y is equal to the square root of x minus the y of this line here. The y of this line, which is x minus 2. That is consistent in this part. Okay? Whereas in here, it's different. So you could see that for area 1, it's different. So we'll check first what's the area that is being written in here. You have here bounded by -1 and 2. So the question is, how did we get this -1 and 2? You can see this limit here. Okay, you have that limit. -1, this is your dy negative 1 to 2. Here y is equal to 2. How did this came about? If I may ask, how did this particular limits came about, the negative 1 and 2, for this area that we have? Paano siya nakuha? What was that? How did negative 1 and 2, how was it determined? Look at the integral this time. It's dy, and this must be x. This is the area that is being referred to in here. We're using a differential element in this pink area. This is now dy, and this is x of the line minus x of the curve. Okay, the x of this line minus the x of the curve, and you multiply it by 2, or you can have only one. Limit would be from negative 1 to 2. But the question is, how was this particular limits or set of limits determined? How was the set of limits determined? If I may ask. Sige. Equate both equations in terms of x and substitute. Okay. Actually, that's correct, Carlos. Actually, whether you equate in terms of x or in terms of y, you will still be getting actually the y, even if you start with x, because in terms of intersection, you always have x and y. All you have to do is substitute. Whichever of the two procedure is easy for you to accomplish. So in this case here, your equation here is in terms of y, which is x minus 2, and you have here a y, which is y squared, which is x. So budlay siya nga ang imo nga y in terms of x mo, because you will have a square root of x. So better get an equation of x in here and equate the x of the other one. What I mean, if you express your y here in terms of x, the result would be y equal to square root of x. If you equate it with this one, that would be a little bit cumbersome and complex for some maybe, because your square root of x will be equated to x minus 2. So better yet, as suggested by Carlos, it's the x that you will equate. So you already have the x in here. Your equation y equal to x minus 2, you represent or you rewrite where y is expressed in terms of, or rather x is expressed in terms of y. So what do I mean by that? You keep the x here, so you have x, and then you will have it equated to y plus 2. You transfer this negative 2 on the left side. Now you have both in terms of x, so you can have now this x, which is y squared, you equate to this x, which is y plus 2. So you will have actually a quadratic equation in y. Okay? So you have y squared minus y minus 2. This is factorable, right? So you have y minus 2 times y plus 1 equal to 0. Right? The factors of y squared minus y minus 2 is y minus 2 times the quantity y plus 1. If you'll have it expanded, you'll have this one. So in the process, you'll be getting a y, which is negative 1, and a y, which is 2, after you equate these factors one by one to 0. So you'll be getting this. Do you get it? That's the reason why you will have here a negative 1 to 2. So you'll have the lower limit as negative 1, starting in here to 2. By the way, this area that is written here, what is this area? You have y plus 2 minus y squared, then quantity dy. It's just like you have here, we're so used with, I write it here, area equal to y dx. We're so used to this because our elements are vertical. In this case, since your limits now are in terms of y, it would be now area equal to x dy. So this is your x and this is your dy. How did it came about? Why do you have x for this? You have, imagine, you have -1 up to in here. So it's horizontal. Now, let's check. I'll just erase this one, this part only. We will not erase the solution. Okay? You can have this divided into two regions. In this particular example, since you started with y equal to -1, that's the lowest portion here, and y equal to 2, it's from the lowest to the uppermost portion. What's done is this. We'll have a different, let's hoping that this would be seen because our illustration is very small. So you have a horizontal element. Now, if this is your dy and this is your x, I'll erase this. There's no need for you to have separate areas, although you can still solve it like that. I'll just draw the element again. So your x here would be the x of the line minus the x of the curve. So the x of the line is y plus 2. You see it here, y plus 2, and the x of the curve, which is y squared. So if you use the horizontal element, there's no need for you to, shall I say, separately determine this area and separately determine this area. Only one set of computation. One set of computation, one integral for the entire area. Because if you're in here and in here, it would be still line and curve. If you're here, you have line and curve. If you're in here, line and curve. So in this example now, you see the importance of not getting used to just having the area always expressed as y dx. It could also be x dy. And that if that is the case, your limits of integration would now be boundaries on the y, on the vertical axis, on the y variable, not the x. Do you get it? Although class, pwede gid yang sulbon yung gid siya gyapon nga separate ini kag ini. Depende sa inyo. Pero, my suggestion is, whichever of the procedure will not lengthen your time in solving, digto ka mo, okay, para damo inyo ma-solve pa. Kaysa sa mag-separate ka mo, determines ang areas, tapos i-add nyo pa. And of course, even if you separately determine the areas, you have to make sure that if you use the vertical axis or the horizontal axis, the vertical or the horizontal differential element, it has to be consistent on the area that you have chosen. So in the integral that was shown to you, there's no need for you to separately determine area 1 and area 2. Only one horizontal differential element already determines the area bounded by this region here in blue. No need to have it separately determined like this. Do you have any questions? You can also have as an exercise class, okay, this is part I may have. You can also have as an exercise as suggested, determine this area here. If you really like the vertical element, so you will have vertical element here. And in here, gaso diri mo horizontal element kagit. Okay, kung mag-vertical ikaw, that should be curve minus curve. You will have nothing to integrate. So it should be horizontal. So rather than having to determine two areas and get the sum, why not just use one horizontal element for the entire area? This is our entire area. So isa na lang dito horizontal element. That way, you will save time in your computation. So amo na lang din siya. Like that. Okay, kung ma-separate ka pa, you will have here vertical. and you will have your horizontal. So that would take time. Hindi ka di pwede ka horizontal. Erase again ha, para makita nyo. Para makita nyo yung point ko. Hindi ka di ka horizontal sa area 2 only. Because if you use horizontal only here, you will have here line and curve. Pero dereo, look, you will have this slant line and you will have this vertical line. So, masakit pagid ang ulo nyo. So, ang dapat sa area 2 nga strip, if you're going to separately determine the two areas is vertical. So, dapat din sa area 2 nyo vertical ang inyo strip. That is, if you will determine again the area separately and then get the sum. But this solution is just determining the entire thing all at once. So, isa lang. You have dy, and this is your x. So, when you determine the x class, it's from the rightmost part to the leftmost part. Okay? So, you have here the y of this line, and rather the x of this line, and the x of this curve. X of this line and the x of this curve. If it's vertical, the y of this curve minus the y of this line. Do you understand? Do you have any questions? Point of clarification? Then, sige. Excuse me. So we will proceed if there are no questions. Now we go to sample number 7. Determine the area enclosed. Determine the area of the enclosed area by, so this is your x equal to 1/2 y squared minus 3 curve. This is your parabola opening to the right. And this is your line x minus 1. So the area actually is this region here. The safest way of determining the area is using the horizontal. Using the horizontal element. Differential element. So if you use the horizontal element, it would be something like this. There's no need to determine separately the areas of this yellow region and this pink region. In here, if you do it like this, you will only have one differential element for the entire area. So this is your dy, and this is your x. So x of the line minus x of the curve. So if you're going to set up your equation integral here, I'm just going to show to you because the solution here is different. You will have the x of this line, which is y plus 1. I'm taking it from here. X is equal to y plus 1. And the x of this curve. So minus this entire expression. 1/2 y squared minus minus, so plus 3 dy. So you have to determine what is the y coordinate of this point. So you have, by the way, already have it determined here. So it's starting from y equal to -2 to y equal to 4. 5, 4. Point of intersection and -1, -2 to 4. So if you will simplify, your integral from -2 to 4 will be, I'll just rearrange it, 1/2 y squared plus y for this, and 1 plus 3, that would be 4 dy. This is your integral. And this would be now the area of this region here. Okay, I'll give you 2 minutes. Can you please determine that area? And we will compare it to the one that is using a different procedure below. Can you please solve? Just type on the chat box if you have the answer already. For this area here, we're using the horizontal element. You will evaluate this integral. The integral that you have here, the area will be equal to, this is negative 1/2 y squared. So if you use power rule, that would be negative y cubed, right? Y cubed divided by, so you have 2 here, so that would be 6. So y cubed over 3. And then for this one, you will have y squared over 2. And for the 4, you will have 4y. Your limits will be negative 2 to 4. Or you can use your calculators to do that for you. It can readily give you the answer. Okay, can you do that? I can't find my calculator here. If you will substitute, so you have to substitute 4 first. Write it here. 18, Cassie. Okay, thank you, Cassie. Okay, actually, the answer is 18. It has to be the same as this one here, which uses a different procedure. So hopefully everybody will get the 18. I already gave you here the answer to the integration. So you just supply the limits 4 for the upper limit and negative 2 for the lower limit. Okay? Now, to save us some time, the procedure that I have illustrated in here for you is using the horizontal strip, which is more straightforward. But for others, it could also be like this. You divide it into 2 regions, the yellow and the pink region. Now, I will erase first the upper part. Now, let's say this is our this is our area 1 and this is our area 2. Now, notice what is written here. It's dx. So meaning it's the vertical strip that is being used. You have one here below and you will have here on top. This particular area is the same. One is the mirror of the other. So you can use either the top portion or the low portion and then multiply it by 2. This is what happened in here. So you have the square root of 2x plus 6 minus the square root of 2x plus 6. So you have 2 square root of 2x plus 6. But why is that? You have determined only actually this integral, this one term here, determines only the area of just one part of this pink region. If you will determine the 2 areas, you will have to multiply it by 2. Or you have to add the square root of 2x plus 6 to another 2x, square root of 2x plus 6. But the question is why? So remember, you're using here the vertical strip. So you will have here y dx. So meaning the y here, the equation of the curve that you need is y in terms of x. So, but your equation is x in terms of y. So you have to derive that equation in here. The first thing you do is, of course, transfer the 3 on the left side. So that would be plus 3. And you will be left with 1/2 y squared here on the right. Then cross multiply 2. That would be 2x plus 6. 2x plus 6 equal to y squared. And since it's just y that you need, so your y is equal to the square root of 2x plus 6. Get it? So if your differential element is here below, that would be the y of this line minus the y of the curve, right? But since this is in the lower part of the x-axis, that would be negative, the negative of the negative. So that is why you see here, positive. Since this y of the curve is square root of 2x plus 6, so you just added it to another square root of 2x plus 6 here. Because it's just like you're getting the area of one region and you're multiplying it by 2. And that would be this part in here. And since you're using dx, you have to be careful that your limits here should also be in terms of x. So for the pink region, your x starts with -3 and ends with -1. -3 and to -1. And that is true because it starts here from -3 to -1. Okay? Y dx for this particular region. What about this? So you can also use here the vertical strip, but this one no need to multiply by 2. Okay, there's no need to multiply by 2 because you have here the y of the curve minus the y of the line. And it's consistent in whichever location you're going to plot your differential element. Okay, so the y of the curve is square root of 2x plus 6. The y of the line, this is your line, is x minus 1. So minus. Your limit, take note, your limit will start with x -1 to x equal to 5. Here, the x of the farthest most to the right intersection point. Okay, so your limit is -1 to 5. So from here to here, it's -3 to -1, pink region, to the in your yellow region, it's -1 to 5. If you process the integrals here, it would give you the same answer as you got when you use the horizontal element. So actually, it's really cumbersome. This particular procedure is really cumbersome compared to the one that I have illustrated to you. But nonetheless, just to show to you how you use the process of multiplication, this one is just like you multiplying the area of this one region by 2 because you have added the other one. And in here, you have this area using the vertical strip just like this one. So that's another procedure for you. Okay, but if I'm going to be asked, of course, the first one that I have shown to you is more straightforward. Okay? It's more straightforward and it's not time consuming and it's not prone to error. Hindi siya, ang risk mo of committing errors is lesser because the process is shorter. The longer the process, the greater the probability that you'll be committing error. The shorter the process, as long as you understand what you're doing, the lower the risk of you committing the error. Okay? Do you have any questions? No question? Sige, I hope that it's clear because you're not asking questions. We'll continue with the next. So this one is the one wherein you're using the horizontal strip, the one that I have illustrated to you. So you'll be getting an 8. Okay? Still using the same points of intersection. Only that you're using the y. So from -2 to 4 here. Now area between two curves. So this is the principle now. Outer function minus inner function. Like if you use the vertical strip in here, this is your y and this is your dx. So you will have y1 minus y2 for your y. This is your y actually. And you have dx. It's bounded here by a and in here by b. Okay? If you use the vertical strip. You can also use the horizontal strip. However, you will have now x here and dy. So in terms of y, your limits will be c to d. And instead of y's, you will have x. So farthest most, this one. So that would be x1 minus x2. Okay? If you're determining the area between two curves. Question? So it's important, class, that you know how to determine this point of intersection. How? You just equate the two equations. Whether if it's easier to equate the y's, then equate the y's. If it's easier to equate the x, then equate the x. Doesn't matter which of the x or the y you determine first. Anyway, you'll get the other one once you have the, you'll get the x once you have the y, or vice versa. You'll get the y once you have the x. How? So if you already have the x, you just go back and substitute it on the equation of the curve and you will have the y. Or if you get the y, you just substitute it in the equation of the curve, it would have, you will get the x. The question is, Miss, diin sa duwa ka equation any? Because if it's a point of intersection, class, we go back to the principle again that at the point of intersection of the two curves or of the two functions, they will have the same x and y value. So either this equation I'll use or this equation I'll use at this particular point, they will have the same x and y. At this particular point, they will have the same x and y. So it doesn't matter in which equation you will substitute the computed x or y value that you got when you equate the two in order for you to determine the coordinates of the points of the intersection. And this one is for x. Question? Check it. You'll clear the markings. You have this. So the same thing, you can have a vertical element here. So if it's vertical, this is dx and this is y. So the area will be y dx. And since it's x, having x bounded by xa, x equal to a and x equal to b. What is the y? That would be f of x minus g of x dx. F of x, this is the equation of the upper curve. G of x is the equation of the lower curve. Okay? Either which you like to interpret it, you're bound to get the same answer as long as you don't stay away from the principles. So the red shaded area or the So the same applies with this scenario here. We'll have this a dx and we have y. So still the same principle. So area is equal to this f of x minus g of x dx. Interval is from a to b. So you start with a equal to x equal to a and end with x equal to b. Upper minus lower portion. So it's function of x minus g of x. Don't stay away from that principle. It still will give you the same answer. Here my markings. Let's see what's it. For this one, the same thing. F of x minus g of x, still vertical. Dx, y. So area is f of x upper minus g of x lower. Limit would be from a to b. You may wonder why always vertical axis is because if you use the, or rather vertical differential element. Why use it? Because you can see it's consistent. Plus, wherever you place that vertical element here, you will have this f of x minus g of x. It's the same thing with this one. You can use a differential element for your area if it's not consistent in your area of concern. Let's say, ang boundary, bala nila, hindi consistent. So, hindi mo na magamit. So, kinalang consistent siya. Okay. Here my markings. Interrupt me if you have questions. Note that function of x comes first as f of x is higher, is the higher function, and f of x is greater than g of x for all points in the required domain. So as I've said, don't sway or don't swerve away from the principle. It's always highest point minus lowest point. Farthest point to the right to the leftmost point if you're using the horizontal differential. element. What about this? What would be your approach here if I'm going to ask? What's the approach? What will you do? Anybody? Any suggestion? What will you do? You can just outline your procedure by means of an explanation, probably a sentence or two. You'll be done. Just to illustrate that you understood the process of determining the areas between functions. These are functions, function of x and g of x. What will you do? Okay. Separate it section 1, 2, and 3. Very good. Separate sections 1, 2, and 3. What element will you use? So Carlos already answered. What element is appropriate in this case? So Carlos said, determine area 1. Determine this, area 1. Area 2, and this is area 3. Very good. Of course, you have to do that because you cannot just have one computation here for the 3. Then, my next question is, what's the appropriate differential element here? Vertical or horizontal? What differential element or area will you use? Vertical or horizontal? Make sure that it's consistent for the areas that you are considering. Oh, it's as if it's only Carlos and me again. What differential element will you use? Cassie, no, not Cassie is here. Eugenie, what differential element will you use?
Vertical, miss.
Correct. Very good. So, you are to use the vertical. Why will you use the vertical? Because if you use vertical here, it's consistent. Huh? Your upper curve is f of x, your lower curve is g of x. So it's always f of x minus g of x. F of x minus g of x. So that's okay. Same thing in here. It's g of x minus f of x. It's g of x over minus f of x. In here, it's g of x minus f of x. So 3 separate areas which you need to take the sum of and use the vertical element. Okay? In that domain, x greater than a and x less than or equal to b, the curves cross over twice, therefore 3 separate areas. So check to si Carlos. 3 separate areas need to be calculated, noting that g of x is greater than the function of x in regions 1 and 3. Your g of x is higher than your function of x, but it's different with the one in the middle because your function of x is higher than g of x. So what should be our formula? This is our formula. So you'll have for this region bounded by a to c sub 1 for the x, it should be g of x minus f of x dx. For region 2, that would be f of x minus g of x because f of x is higher, bounded by c sub 1 to c sub 2. And in the third region, you will have c sub 2 to b. So this is c sub 2 to b. And then the manner of subtraction is g of x minus f of x. That's it. You just place in there the values or the expressions for g of x and function of x and integrate. So I think this would be our last for the afternoon. Find the area bounded by the functions y equal to 4 over x, y equal to x, and the vertical lines x equal to 1 and x equal to 3. Now, there are problems class that are like this. It will just simply discuss to you the area that you need to determine, but it will not give you an illustration. So what would you do? Excuse us, huh? So you have to first plot. How would you plot? Simple class. You just assign values of x here and so for y. For this line, you need 2 points. This line is very easy because whatever is your x, that would be also your y. So 2 points for that. It is said that you have in a line at least 2 points, but of course there are infinite number of points in a line. You just need 2 points, so you can draw these 2 lines and then also draw these 2 vertical lines. Okay, and check how will the area be, or what would your area look like. So draw. Okay, this is your y equal to x, and note x is equal to 1 to x is equal to 3 is the required domain. So in here, if it's 1 to 3, if I'll initially draw it here, it's in here class. This is x equal to 1, 1, 2, 3. This is x equal to 3. This is your y equal to x. I'll just use black. So this is your y equal to x, and this is your curve. Y is equal to 4 over x. So what do you think is the region that we're interested in here? Just continue the red part here. Continue. And then we'll extend the black part of the curve. Okay. So what is the area that we're trying to find? It would have been easier if you're on face-to-face, but what do you think is the area that we're trying to find between x equal to 1 and x equal to 3? The area is what? Sige. Because I'm Lenny, I'm for Lenny. So you have this one class, and you have this. Bounded by this line, the curve, and this one, this line, the curve, and this one. Okay, we'll go to the next and just close this one. Shade area. See, this is the area. Okay, so what is this point here of intersection between y equal to x? This is your line, y equal to x, and your curve, y equal to 4 over x. Black. This is 4 over x. So what do you do to find these two here? So this is actually, this is 1 and this is 3, but you need to determine this. It's just determined for you in here. It's 2. How will you do that? Just like what we've done in the previous examples, you equate the function. So you have y equal to x, this line, and this curve, 4 over x. So I'll equate the two y's. So x is equal to 4 over x. X squared is equal to 4. So x is equal to 2. That's the reason why we have here. Do you follow? So the area that we're after is this area and this area. If you use a vertical element, actually it will be consistent in both areas. However, this one is different. The y in here is different than the y in here. I hope I make sense. Okay? So you're still going to use the x as the limits because you have here from 1 to 3 and you have here somewhere in the middle which is 2. So you will have two separate integrals to evaluate and you have to take the sum of the two. Okay, Before I proceed, you have any question here? Okay, so I'll clear my markings. We proceed to the next one. Let's set up the integrals. This is your integral now. I'll go back, huh? In here, in this part here, it's 4 over x minus x. In this part here, it's x minus 4 over x. So in the two separate sections, the boundaries are the negative of each other. You have this 4 over x minus x. Here it's x minus 4 over x. The limit here is 1 to 2. In here it's 2 to 3. Okay? 1 to 2, 2 to 3. So if you will evaluate, you will have LNs now, you'll have power rule. Nothing to worry, I know you know how to do that. So you'll have here your answers, and the area of the two shaded regions is 2.15 square units. Okay, so you have two areas to determine. Oh, I still have 9. So find the area below. Function of x is negative x squared plus 4x plus 3. And g of x is the area below function of x and above g of x over the interval 1 to 2. So these are the areas that we are to determine in the different scenarios. So better yet class, just like what I have shown to you already, this is just for additional exercises. Draw just one vertical element here. Okay. So this is your g, this is your function of x, and this is your g of x. This is your y, you'll have dx. So it will be bounded here on x equal to 1 to x equal to 2. 1 to 2, function of x minus g of x. Okay, it's just like taking the area of this, subtract the area of this. That would be the area in between the two curves. Nothing different than the one that was already shown to you in the previous example. Okay, and the answer is 49 over 12. Anyways, I have shared all of these documents already under lessons for module 3. So you can review again and better work it out on yourself and check whether you can do it on your own. Hopefully, this is the last class. Example 10. Find the area between the function and the g of x over the intervals 0 to 1. So you have two separate areas again. You have this area and you have this area. You need to find this point of intersection. So you have to equate this negative x squared plus 4x to x squared minus 6x plus 5, giving you these 2 points of intersection, or rather this single point of intersection. So you will have 4x, 5 plus minus square root of 15 over 2. So whichever of the two lies above the x-axis, then that would be the x that you will use. In this case, that would be, let me check. You will have, if this is square root of 15, 5 plus the square root of 15 divided by 2, that would be 4.43. But if it's 5 minus the square root of 15 divided by 2, you will have 0.563. In this case, class, the answer which is 0.563, you cannot choose that. You can choose that one because it's between 0 and 1. You will have two answers here. 0.45. Let me erase this. 564. And you have another one, which is if you're going to add 5 plus square root of 15 divided by 2, that would be 4.4365. Now, if you'll be asked, which of the two x's will you use? This one or this one? I'm going to ask you, which one will you use? Since you are to have the intersection of these two curves between 0 and 1, you could see it here, between 0 and 1, you cannot use this. Why? Because it's beyond 1. So you are to choose this one, the 0.564, because it's between 0 and 1. So this must be x equal to 0.564. Okay, I hope we have understood why we have to choose this one over this. Okay, I probably chose this particular example to be included because this is the case wherein you are to validate which of the two values that you have computed will apply for the given situation that you're given. So the 4.4365, though it's also an x coordinate for the intersection of the two curves, it is not between 0 and 1. And we are to determine the area on the interval 0 and 1. So the x that you will use is 0.564. Okay, so if you already have that particular point of intersection, I know you know what to do. You just get this area here and this area here. So for this area, your limit will be 0 to 0.564. For this area, that would be 0.564 to 1. You will still use the vertical elements because that would be easier to, or that will make rather a consistent representation of your differential element. So you'll have the same y here, in any portion, same thing in here. So the same. So you use the vertical elements. This is dx, and you also have y here. Okay, I'll clear my markings. Zero to a. That's the a that we're determining, and this is a to 1. So whatever the value of a is. This is your answer. I leave the remaining examples here. It will be a repetition of the other principles that were illustrated to you in the previous examples, just for you to have more material to study. So this is example 11, wherein you have 3 regions also to determine the area of. So you can have the 3 separate regions computed, the area, and then get the sum. This is example 12. What is good about this is your function now is trigonometry. But you know how to determine the integral of trigonometric functions. So it's actually easy. They are just fundamental trigonometric functions. Okay, so any questions? You have 12 examples on areas. When we meet each other next week for on Monday, I will not